Imagine a planet where the sun does not rise. Not metaphorically, literally. The sky is so filled with dust, soot from burning forests, and sulfuric aerosols that sunlight simply does not reach the surface. Plants cannot photosynthesize. Temperatures drop by 25 degrees Celsius, about 45 degrees Fahrenheit. Acid rain dissolves the shells of marine organisms. Food chains collapse from the bottom up. First the plankton, then everything that ate it, then everything that ate that. This lasts not 1 day and not 1 year. By various estimates, between 5 and 15 years. And then the winter ends. And what came after was even stranger. This is the story of 100 years after the asteroid. What happened to the planet? And who survived it? And why exactly them? Before we go any further, please subscribe to this channel. Your support really helps us to continue this work. Thank you. There is a common misunderstanding about the Chicxulub impact that shapes how most people think about the end of the dinosaurs. The misunderstanding is this: that the asteroid killed the dinosaurs directly, that the impact itself, the explosion, the fireball, the earthquake, was the mechanism of extinction. This is understandable. The energy released in the first second of the impact was roughly 1 billion times greater than the atomic bomb dropped on Hiroshima. The crater it left, now buried beneath the Yucatan Peninsula and the Gulf of Mexico, is approximately 180 kilometers, about 112 miles, wide. The impact was, by any measure, one of the most violent events to occur on the surface of this planet in the past several 100 million years. But the impact itself killed relatively few organisms compared to what followed it. The organisms within a few 100 kilometers of the impact site were incinerated instantly. The mega tsunami that radiated outward from the impact zone devastated coastal environments across the Gulf of Mexico and the Atlantic within hours. But the vast majority of the 3/4 of all species that went extinct over the following months and years did not die because of the impact itself. They died because of what the impact set in motion, a cascade of environmental consequences that unfolded over decades and that collectively constituted one of the most comprehensive transformations of Earth's climate and chemistry in the past 66 million years. This is the story of those consequences. Not the impact, the aftermath, the 100 years that remade the world. To understand what happened in the hours, days, and years after the Chicxulub impact, you need to understand what the asteroid actually hit. The Yucatan Peninsula in the late Cretaceous was not granite or basalt. It was a thick sequence of carbonate and sulfate rocks, including enormous deposits of anhydrite, a calcium sulfate mineral. This geological accident turned out to be enormously consequential, because when the asteroid vaporized this rock, it did not merely produce dust and debris, it produced chemistry. The sulfur in the anhydrite was released into the atmosphere in quantities that had never before been injected into the stratosphere in a single geological instant. January 2025, research by Rodiochkina and colleagues from Utrecht University, using new drill cores from within the crater itself, combined with global chemical profiles across KPG boundary sediments worldwide, produced the first empirical estimate of the total sulfur released by the Chicxulub impact. Their findings revised previous estimates significantly. The sulfur release was substantial but less extreme than some prior models had projected, which has important implications for the duration and severity of the impact winter that followed. But before the sulfur aerosols had even fully dispersed into the stratosphere, the first and most immediately lethal consequence of the impact was already underway. In the hours after the asteroid struck, the material it had vaporized and ejected was re-entering the atmosphere across the entire planet. The impact had thrown billions of tons of molten rock into ballistic trajectories that carried them above the atmosphere and then back down across every continent and ocean on Earth. These particles, called spherules, tiny droplets of solidified melt, re-entered the atmosphere at high velocity, and the friction of their re-entry heated the upper atmosphere to temperatures that, in some models, approached 100 degrees Celsius, about 212 degrees Fahrenheit, across large areas of the planet. The mechanism is similar to the way a spacecraft heats up on re-entry, but operating simultaneously across the entire sky, rather than along a single trajectory. The result was an intense pulse of infrared radiation delivered to the surface from above. Not fire in the conventional sense, but radiant heat that could ignite vegetation and kill exposed organisms without any direct contact with flame. The geological evidence for this thermal pulse is preserved in the boundary sediment layer that marks the KPG boundary worldwide. A thin layer of carbonized plant material, charcoal, appears at or immediately above the iridium-rich clay that marks the impact globally, and it is found on every continent. Forests burned from North America to Asia. The fires were not started by sparks or embers traveling thousands of miles from the impact site. They were started by the sky itself, heating to temperatures sufficient to ignite organic material across the entire hemisphere, exposed to the re-entering ejector. The Tanis fossil site in North Dakota, a remarkable deposit discovered and described by Robert De Palma and his colleagues, preserves the immediate aftermath of the impact in extraordinary detail. The site shows a surge of water and sediment that arrived within hours of the impact, carrying with it a mixed fauna of freshwater and marine animals, glass spherules from the impact still embedded in the gills of fish that died in the surge, and evidence of a world that went from ordinary Cretaceous afternoon to global catastrophe in the span of a single day. The fish at Tanis are, in a very real sense, the most precisely dated casualties of the Chicxulub impact. Animals that were alive on that ordinary Tuesday and dead within hours, their bodies preserved in the sediment of the most consequential day in the history of vertebrate life. By the end of the first day, the world had already changed irrevocably. The fires were burning across the northern hemisphere. The atmosphere was loading with combustion products, carbon dioxide, carbon monoxide, and most critically, fine carbonaceous soot particles that would prove far more important to the subsequent climate change than the impact dust alone. The crater itself, 180 kilometers across, was still cooling. A lake of impact, melt and steam. The center of the most energetic geological event the planet had experienced in hundreds of millions of years. And in the sky above, the stratospheric injection of material was just beginning its work. What happened to the atmosphere in the days and weeks following the impact is the story of how a single geological event can restructure the chemistry of the entire planet. The material injected into the stratosphere, the dust from pulverized rock, the sulfur dioxide from the vaporized anhydrite, the soot from the global wildfires, entered a region of the atmosphere where normal weather systems cannot reach. The stratosphere has no rain, no precipitation, no mechanism for washing particles out of the air on human timescales. Particles that enter the stratosphere can remain there for years, slowly settling out over timescales determined by their size and by stratospheric circulation patterns. The finest particles, the submicron soot particles from the wildfires and the sulfate aerosols converted from the SO2 by stratospheric chemistry, were the most persistent and the most effective at blocking sunlight. The soot is crucial to understanding the impact winter, and its importance has been increasingly emphasized in research over the past decade. A study published in 2017 and elaborated in subsequent years proposed that the soot from the Chicxulub wildfires, specifically the fine soot particles produced by the burning of hydrocarbon-rich vegetation, was actually more important to the global darkness than the mineral dust from the impact itself. Mineral dust settles out of the stratosphere relatively quickly, within months to a few years. Fine soot particles, being smaller and lighter, settle much more slowly and can remain in the stratosphere for years. The estimated quantity of soot produced by the global wildfires was sufficient in climate model simulations to reduce incoming sunlight to a small fraction of normal values for a period of years. The combined effect of the impact dust, the sulfate aerosols, and the wildfire soot on global photosynthesis was catastrophic. Within weeks of the impact, the amount of sunlight reaching the Earth's surface had fallen to levels insufficient to support photosynthesis across most of the planet. This was not a gradual transition. It was an abrupt shutdown. The phytoplankton in the surface ocean, the microscopic algae that form the base of nearly all marine food chains, could not photosynthesize in the near darkness. Their populations collapsed within weeks to months of the impact. The zooplankton that fed on the phytoplankton followed. The small fish that fed on the zooplankton followed. And so on, up through the food chain, each collapse accelerating the next. On land, the shutdown of photosynthesis was equally comprehensive. The forests that had survived the thermal pulse, those in the southern hemisphere that had been on the opposite side of the planet from the ejecta thermal pulse, or those in regions where the thermal pulse was less intense, now faced a different threat. Without sunlight, they could not photosynthesize. Without photosynthesis, they could not grow new tissue or maintain the metabolic processes that keep plants alive. Within weeks, even living forests began to die. The leaves fell. The canopies thinned. The understory, already stressed from the thermal pulse and the fires, stopped regenerating. The temperature drop that followed the photosynthesis shutdown was significant. Climate models have variously estimated the peak cooling of the impact winter at between 20 and 25 degrees Celsius, about 36 to 45 degrees Fahrenheit, below the pre-impact Cretaceous baseline in some continental regions, though the global average temperature drop was somewhat lower, perhaps 10 to 15 degrees Celsius, about 18 to 27 degrees Fahrenheit. The Cretaceous world had been warmer than the modern world. Average global temperatures in the late Cretaceous were perhaps 8 to 10 degrees Celsius, about 14 to 18 degrees Fahrenheit, higher than today, with no permanent polar ice caps and shallow, warm seas covering much of the continental interior. Even with the impact cooling, the world did not necessarily freeze solid everywhere. But the cooling was severe enough to fundamentally disrupt the functioning of ecosystems that had evolved in the warm, stable conditions of the late Cretaceous. The sulfuric acid rain deserves particular attention as one of the more chemically precise consequences of the impact. The sulfur dioxide released by the vaporization of the anhydrite rocks was converted in the stratosphere to sulfate aerosols, droplets of dilute sulfuric acid suspended in the upper atmosphere. These aerosols served a dual purpose in the aftermath. They contributed to the blocking of sunlight, adding to the darkness of the impact winter, and they were eventually rained out of the atmosphere as acid precipitation. The ocean surface acidification that followed is documented in the chemical record of the KPG boundary. Boron isotope measurements in foraminifera, the tiny shelled single-celled organisms that are among the most sensitive recorders of ocean pH in the geological record, show a rapid decrease in surface ocean pH of approximately 0.25 units within the first 1,000 years after the impact. This is a significant acidification event by any measure, and it had direct consequences for the calcareous organisms, those that build their shells and skeletons from calcium carbonate, that were already under stress from the collapse of photosynthesis. The acidification worked against calcification in a precise chemical way. Calcium carbonate shells dissolve in acidic conditions. Organisms that needed to build and maintain carbonate shells were doing so in an ocean that was actively trying to dissolve those shells. The energetic cost of shell building increased dramatically. Many organisms that had been perfectly adapted to the warm, alkaline oceans of the late Cretaceous simply could not maintain their calcification in the new chemical environment. The consequences for marine biodiversity were immediate and severe. The ammonites, the coiled shell cephalopods that had been among the most abundant and diverse marine invertebrates of the Cretaceous, went extinct. They had survived multiple previous extinction events, including the late Devonian and the end Permian. But the combination of photosynthesis collapse, temperature drop, and ocean acidification proved too much. Their larvae, which depended on plankton for food, starved in the darkness. The adults, which depended on the entire marine food web for their own sustenance, died as that web collapsed around them. The ammonites are perhaps the most vivid example of an organism that had been superbly adapted to the Cretaceous world and was simply unable to adapt to the world that the impact created. The fungal spike that appears in the sediment record immediately above the KPG boundary is one of the most telling indicators of what the terrestrial world looked like in the weeks and months after the impact. In the sediment layers immediately above the thin iridium-rich clay that marks the boundary globally, paleobotanists find an extraordinary abundance of fungal spores, a concentration so far above background levels that it can only be explained by a massive proliferation of fungi in the immediate post-impact environment. This fungal spike reflects the ecological reality of a world in which vast quantities of organic matter had suddenly become available for decomposition. The forests that had burned, the animals that had died, the marine organisms washing onto shores, all of this represented an enormous substrate for decomposers. The fungi were not casualties of the impact winter. They were among its primary beneficiaries, at least in the short term. For the small omnivorous mammals that had survived the impact in their burrows and root systems, this fungal proliferation was not a disaster. It was a food source. Seeds in the soil, insects in the litter, fungal matter on the surface of decaying wood. These were the resources that sustained the survivors through the darkest and coldest years of the impact winter. The mammals were not passively waiting for the world to recover. They were actively foraging in the devastated landscape, exploiting whatever remained available. Their dietary flexibility, the same flexibility that had allowed them to survive as marginal animals in the dinosaur-dominated Cretaceous, was now their primary competitive advantage in a world where the dominant animals were dead or dying. The collapse of the marine food web deserves a more detailed account than the summary version suggests, because the sequence of collapse was not simultaneous. It proceeded in layers, each one following the one below with a lag that reflects the generation times and metabolic rates of the organisms involved. The phytoplankton were the first to go. Their populations collapsed within weeks of the impact, as light levels fell below the threshold for photosynthesis. The zooplankton, the tiny animals that graze on phytoplankton, followed within weeks to months, their food supply gone and their populations crashing. The small fish and invertebrates that fed on zooplankton followed over the subsequent months. The larger fish and marine reptiles that occupied the upper trophic levels of the Cretaceous marine food web found themselves in an ocean that could no longer support them. The mosasaurs, the large predatory marine lizards that had been the apex predators of the Cretaceous seas, had nothing left to eat. The plesiosaurs faced the same problem. They were not small animals that could survive on scraps. They were large, metabolically demanding predators in an ocean whose food web had collapsed from the bottom up. The geological record of the KPG boundary in marine sediments is one of the most striking visual documents in all of paleontology. A section of limestone or chalk deposited in the Cretaceous shows a rich and diverse assemblage of microfossils, the shells of foraminifera, the plates of calcareous nanoplankton, the fragments of larger organisms, that reflects the productivity and diversity of the late Cretaceous ocean. And then, at the boundary clay, the diversity drops to almost nothing. The centimeter of sediment immediately above the iridium layer contains almost no carbonate fossils. The organisms that had been producing them were gone, and the few survivors were not yet calcifying in sufficient quantities to leave a record. The ocean went, in geological terms, essentially silent. The chemical conditions in the surface ocean in the years immediately following the impact were, in addition to the acidification, deeply anoxic in some regions. The collapse of photosynthesis removed the primary source of dissolved oxygen in the surface ocean. As the dying organic matter of the Cretaceous ocean sank and decomposed, the bacterial decomposition consumed oxygen faster than it could be replenished. Hypoxic and anoxic conditions spread through portions of the surface ocean, adding oxygen depletion to the already severe stresses of cold, darkness, and acidification. The organisms that survived in the ocean were those that could tolerate low oxygen, low light, low pH, and low food availability simultaneously. A combination of stresses that eliminated most of what the Cretaceous ocean had produced over the previous tens of millions of years. The acid rain on land had consequences that extended beyond the immediate chemical damage to organisms. Acid precipitation dissolves nutrients from soil, calcium, magnesium, potassium, leaching them into rivers and eventually to the ocean. In the years after the impact, the intense acid rain events that accompanied the fallout of sulfate aerosols from the stratosphere stripped nutrients from the already damaged forest soils. The trees that had survived the thermal pulse and the darkness were now growing in increasingly nutrient-depleted soils, their recovery further compromised by the chemical damage to the soil ecosystem. The mycorrhizal fungi that normally assist plant roots in nutrient uptake were themselves disrupted by the acidification and the temperature extremes. The recovery of the forests was not simply a matter of waiting for the light to return. It required the reconstruction of an entire soil ecosystem that had been chemically damaged and physically disrupted by the combination of fire, acid rain, and cold. The earthquake and volcanic activity triggered by the impact added additional complexity to the post-impact environment. The Chicxulub impact was energetic enough to trigger earthquakes of magnitude 10 or greater across the planet, the largest seismic events the Earth had experienced in the geological record of the Phanerozoic. New evidence published in the past several years suggests that the mega-earthquake triggered by the Chicxulub impact shook the Earth for months after the initial impact, with seismic waves reverberating through the planet's interior and generating additional tsunami activity at coastlines far from the impact site. The Deccan Traps volcanic province in what is now India, already erupting at the time of the impact, appears to have been significantly stimulated by the seismic energy of the Chicxulub impact, with eruption rates increasing substantially in the years immediately following the impact. The additional volcanic CO2 from the stimulated Deccan eruptions contributed to the carbon dioxide pulse that would eventually drive the post-impact hypothermal, another layer of complexity in the chain of consequences that followed from the single event of the impact itself. The nitrogen chemistry of the atmosphere was also affected by the impact. The enormous energy of the impact was sufficient to force the reaction between atmospheric nitrogen and oxygen, normally a reaction that requires the extreme temperatures of lightning bolts, across vast volumes of the atmosphere simultaneously. The resulting nitrogen oxides, the same compounds produced by industrial combustion and lightning, are precursors to nitric acid, adding another component to the acid rain that fell in the aftermath of the impact. Nitric acid rain is chemically distinct from sulfuric acid rain and affects different aspects of soil and ocean chemistry. The combined effect of sulfuric and nitric acid precipitation represented a chemical assault on the surface environment of the planet that had no precedent in the geological record of the Phanerozoic. Now here is where the story becomes genuinely strange, and where the most recent science has revised what we thought we knew. For decades, the dominant model of the impact winter assumed a relatively simple sequence: impact, darkness, cold, recovery. The darkness lasted perhaps a year or two. Temperatures recovered over a decade, and the world gradually returned to something like its pre-impact state. This model was based partly on analogy with nuclear winter scenarios from the 1980s, and partly on early modeling work that has been substantially revised as more sophisticated climate models and better empirical data have become available. The revised picture is considerably more complex, and in some respects more severe in the short term and more interesting in the long term. On the question of cooling, the 15-year winter model that has emerged from recent climate simulations represents a significant extension of earlier estimates. Simulations indicate that the most severe cooling, global average temperatures below the pre-impact baseline by 10 degrees Celsius, about 18 degrees Fahrenheit, or more, persisted for approximately 5 to 8 years. The recovery from this most severe phase took the full 15 to 20 years that more sophisticated models now project. But the recovery was not a return to the pre-impact world. It was a transition to something different. The sulfate aerosols that had contributed to the cooling were eventually rained out of the atmosphere. The January 2025 research by Rodyuchkina's team found that the sulfate aerosols distributed globally and were deposited back onto the Earth's surface in the months to years after impact, with the total sulfur release being less extreme than some prior estimates had suggested. This was important because it meant the acid rain phase was somewhat less prolonged than previous worst-case models had projected. The sulfuric acid rain was real and consequential, but it was not an indefinite phenomenon. It peaked in the first few years after the impact and declined as the aerosols were progressively washed out of the atmosphere. But as the sulfate aerosols were removed, the other atmospheric change that the impact had triggered began to dominate. The carbon dioxide released by the vaporization of the carbonate rocks at the impact site, combined with the CO2 released by the global wildfires, had added a significant pulse of greenhouse gas to the atmosphere. As the reflective aerosol veil thinned and sunlight began to penetrate to the surface again, this elevated CO2 began to exert its greenhouse warming effect. The world did not merely warm back to the pre-impact baseline, it overshot it. The carbon dioxide pulse drove temperatures above the already warm Cretaceous baseline, creating a brief but significant hyperthermal event in the decades following the impact winter. The world went from cold to warm, overshooting in both directions within the span of a human lifetime's worth of geological time. This thermal oscillation, rapid, severe cooling followed by recovery that overshot to elevated warmth, was unlike anything that had occurred in the previous tens of millions of years of stable Cretaceous climate. The organisms that survived it were not those adapted to the stable, warm Cretaceous. They were those that could tolerate dramatic, rapid change in both directions. And here is where the survivors enter the story. The question of who survived the aftermath of the Chicxulub impact is one of the most studied and most revealing questions in all of paleontology, because the answer is not random. The survivors share a set of characteristics that, in retrospect, look less like luck and more like a specific kind of evolutionary pre-adaptation. Not intelligence, not strength, not size. Something more fundamental than any of those things. The most important characteristic of the survivors was small body size. Small bodies have lower absolute energy requirements than large bodies. In a world where the food supply had collapsed from the bottom up, where the photosynthetic base of the food chain had shut down, the organisms that needed the least food per individual were the ones that could survive the longest on whatever food remained available. A small mammal weighing perhaps 20 grams, about 3/4 of an ounce, could subsist on a diet of seeds, fungal matter, insects, and carrion that would be entirely inadequate to sustain a large herbivore or a large carnivore. The large dinosaurs were not killed by the impact directly. They were starved by the darkness. The second critical characteristic was dietary flexibility. The survivors were, almost without exception, generalists. They could eat a wide range of food types, switching between dietary categories as availability changed. The obligate herbivores, animals that could only eat living plant matter, were among the most vulnerable groups because their food supply disappeared almost immediately. The obligate carnivores that depended on the large herbivores were next. The survivors were the omnivores, the insectivores, the seed eaters, the scavengers, the animals whose diets were flexible enough to exploit whatever food was available in the darkness and cold. Seeds are particularly important in this context. Seeds are dormant plant material that does not require photosynthesis to remain energy-rich. And the soil seed banks of the Cretaceous forests represented an enormous reservoir of caloric content that was accessible to small animals capable of digging for them. The third characteristic was the ability to exploit subterranean environments. Burrows provided insulation against the temperature extremes of the impact winter. The soil acts as a thermal buffer, maintaining temperatures well above the frigid surface air, even when surface temperatures dropped dramatically. Animals that could burrow, small mammals, certain reptiles, many invertebrates, were insulated from the worst of the temperature drop in a way that surface dwellers were not. The evidence for this is preserved in the geographical distribution of survivors. Burrowing animals show much higher survival rates across the KPG boundary than non-burrowing animals of comparable size. The crocodilians survived. This is worth pausing on because crocodilians are large animals, far larger than the small burrowing mammals that are typically highlighted in discussions of KPG survivors. They survived because of a specific metabolic characteristic. They are ectothermic, able to dramatically reduce their metabolic rate in cold conditions and survive extended periods without food in a way that endothermic animals of comparable size cannot. A large crocodilian can go a year or more without eating if necessary. In the cold darkness of the impact winter, the ability to simply shut down metabolic activity and wait was a survival strategy that ectotherms could exploit in a way that warm-blooded animals could not. The crocodilians went into a kind of enforced dormancy during the worst years of the impact winter and emerged on the other side largely intact as a group. The turtles survived for similar reasons: ectothermy, low metabolic requirements, and the ability to exploit aquatic environments where temperature swings were buffered by the thermal mass of the water. The freshwater environments that turtles inhabited were fed by organic detritus washing in from the surrounding devastated landscape. And detritus, unlike living plant matter, does not require photosynthesis to be available as food. The freshwater food chain that depended on decomposing organic matter rather than on primary photosynthesis was significantly less disrupted than the food chains that depended on living plants or phytoplankton. The birds survived, partially. Approximately 3/4 of all bird lineages went extinct at the KPG boundary. But the birds that survived appear to have been ground-dwelling, seed-eating forms rather than the tree-dwelling, fruit-eating forms that dominated the late Cretaceous avifauna. The loss of the forest canopy, both to the initial fires and to the subsequent die-off during the impact winter, eliminated the habitat of arboreal birds as effectively as it eliminated the habitat of arboreal mammals. The survivors were the ones that could exploit the ground, the seed banks, and the insect populations that persisted in the soil and litter, even as the canopy died above. The insects survived impressively. Cockroaches, as we have noted in previous episodes, survived the Permian extinction and the KPG extinction with remarkable equanimity. Their survival strategy is ancient and effective: small size, dietary omnivory extended to the point where almost anything organic qualifies as food, rapid reproduction that allows populations to recover from even severe bottlenecks, and the ability to exploit virtually any microhabitat from soil to decaying wood to carcasses. The beetles survived and diversified. The ants and termites, which had been diversifying through the late Cretaceous, survived and would eventually build the complex social colonies that make them, by some measures of biomass, the most ecologically dominant land animals on the planet. The social insect's ability to maintain colony food stores provided a buffer against the immediate food shortage that isolated individuals would have found fatal. The mammals survived, barely in terms of diversity, but consequentially in terms of what they carried forward. The Cretaceous mammals were a diverse group of small, largely nocturnal animals that had been evolving in the ecological margins of the dinosaur-dominated world for over 100 million years. They were, in short, precisely the animals the filter had been designed to select. But they did not merely survive passively. The fossil record of the earliest Paleocene, the period immediately following the KPG boundary, shows that the mammals were already beginning to diversify within the first 100,000 years of the New World, exploiting the empty ecological niches left by the mass extinction with extraordinary evolutionary speed. Now here is where the most recent research fundamentally changes the picture of what happened after the impact winter ended. And it is a revision that makes the story considerably more remarkable than the traditional account. For most of the history of KPG research, the recovery of biodiversity after the mass extinction was assumed to have been slow. The conventional wisdom held that it took millions of years for species diversity to rebuild to pre-impact levels. that the ecological devastation of the impact was so comprehensive that the biosphere required geological timescales to recover. This view was based on the fossil record of larger organisms, the macroscopic fauna and flora whose recovery is visible in the sedimentary record at the million-year scale. But a study published in January of 2026 in the journal Geology by Christopher Lowry, Timothy Bralauer, Kenneth Farley, and R. Mark Leckey of the University of Texas at Austin changed this picture dramatically. Using a novel approach based on helium-3 isotopes, a cosmogenic nuclide delivered to Earth at a roughly constant rate by interplanetary dust, which can be used to calculate the accumulation rate of sediments with high precision. The team was able to date the appearance of new plankton species in the immediate aftermath of the KPG boundary, with a temporal resolution far beyond what conventional biostratigraphy could achieve. Their findings were, in Lowry's own words, ridiculously fast. New species of plankton evolved within fewer than 2,000 years of the Chicxulub impact. Some species appeared within 3,000 to 11,000 years of the impact at different sites. This is not the million-year timescale of conventional evolutionary biology. This is evolutionary change happening at a pace that strains the boundaries of what the mechanisms of natural selection and genetic mutation were previously thought capable of producing. In a world stripped of competitors and filled with empty ecological niches, evolution apparently accelerated to rates that have no precedent in the broader fossil record. The mechanism behind this evolutionary acceleration is not fully understood, but the most likely explanation involves the combination of intense selective pressure, small founding populations, and the complete absence of the competitive constraints that normally slow evolutionary change. When most of an ecosystem has been eliminated, the survivors face a world in which any heritable trait that improves survival or reproduction has an immediate and dramatic effect on fitness. The selection coefficients, the quantitative measure of how strongly natural selection favors a particular trait, become enormous in the post-extinction world. And when selection is strong and populations are small, evolution can move at speeds that seem almost incomprehensible by the standards of stable ecosystems. The crater itself played an unexpected role in the recovery of life, and this, too, is one of the more remarkable findings to emerge from the ICDP Expedition 364 drilling program, whose comprehensive results were summarized in a January 2026 publication in Marine Geology by Gulick and colleagues. When the asteroid struck, it created not only a crater but an enormous hydrothermal system, a network of hot springs and chemically enriched water circulation driven by the residual heat of the impact melt rock. The crater's peak ring, the circular ridge of rock that surrounds the central basin of large impact craters, was permeated by hot water circulating through fractures in the shocked and melted rock. This hydrothermal system provided a warm, chemically enriched environment in the cold, dark years immediately following the impact. The water column above the crater's peak ring appears to have become habitable within days to months of the impact, far sooner than the surrounding ocean. Survivor nanoplankton, tiny photosynthetic organisms that had persisted through the initial dark period in small numbers, were among the first colonizers of this crater environment. The hydrothermal system provided nutrients and warmth that allowed these pioneer communities to establish themselves before the surrounding ocean had recovered. The crater, which had been the instrument of the extinction, became one of the first refugia of the recovery. The most dramatic evidence of this is the recovery pattern documented in the sediment cores from the crater. Primary succession driven by picoplankton in the first centuries after the impact, transitioning over hundreds of thousands of years to plankton-dominated communities more similar to the modern ocean. The terrestrial recovery paralleled the marine recovery in its general character, driven initially by the organisms best suited to exploit disturbed, nutrient-rich, competitor-free environments. The fern spike that appears universally in KPG boundary sections worldwide, a dramatic abundance of fern spores in the first post-impact sediment layers, reflects the capacity of ferns to colonize bare disturbed ground faster than any seed plant, reproducing by spores that can germinate on virtually any substrate. The ferns were the first visible sign of returning terrestrial photosynthesis after the darkness. Behind them came the first angiosperms, germinating from seeds that had survived in the soil through the years of cold and dark. The forests that regrew in the first decades and centuries after the impact were not the forests that had burned. They were simpler, dominated by fast colonizing pioneer species, gradually increasing in complexity as the decades passed and the soil recovered. The mammals that had survived the impact winter was already diversifying into the recovering world. The earliest Paleocene mammal fauna, documented in extraordinary detail in the fossil beds of the Denver Basin in Colorado and Wyoming, shows a rate of evolutionary change that mirrors the accelerated evolution documented by Lowry's team in the marine plankton. New mammalian species appear in the earliest Paleocene sediments, within hundreds of thousands of years of the KPG boundary. Body sizes increase rapidly. Dietary specializations appear. The ecological empty space left by the extinction of the dinosaurs and the loss of 3/4 of all species was being filled by mammalian evolution operating at something close to its theoretical maximum speed. The role of the Chicxulub crater's hydrothermal system in the immediate recovery of life is one of the more remarkable findings of the past decade of impact research, and it was comprehensively documented in the January 2026 marine geology paper by Gulick and colleagues summarizing the results of the IODP-ECDP expedition 364 scientific drilling program. The expedition, which drilled into the peak ring of the Chicxulub crater in 2016 and recovered 829 meters, about 2,700 feet, of core, provided an unprecedented record of both the impact itself and the recovery of life in the crater environment in the immediately following centuries and millennia. The peak ring, the circular ridge of shocked, fractured, and partially melted rock that surrounds the central basin of the crater, was permeated by fractures through which hot water circulated for thousands of years after the impact. The residual heat of the impact melt rock, which in the center of the crater took hundreds of thousands of years to cool completely, drove a hydrothermal convection system that brought chemically enriched warm water to the seafloor and into the water column above the crater. This hydrothermal system provided an environment that was, in the cold, dark years immediately following the impact, anomalously warm and nutrient-rich compared to the surrounding ocean. The biological community that colonized this hydrothermal environment was among the first complex ecosystems to establish itself in the post-impact world. Picoplankton, the smallest photosynthetic organisms in the ocean, capable of surviving at very low light levels, were the primary colonizers. They were followed by progressively larger and more complex plankton communities. As light levels gradually recovered and the hydrothermal system continued to provide nutrients. The succession documented in the crater sediment cores, from simple picoplankton communities to increasingly diverse plankton assemblages over hundreds of thousands of years, represents one of the most detailed records of primary ecological succession after a catastrophic event in the geological record. The implication of the crater hydrothermal system as a refugium is significant beyond its local importance. It suggests that the recovery of marine life after the Chicxulub impact was not simply a passive process of recolonization from whatever survivors remained in the open ocean. It was an active process, driven in part by the specific environments that the impact itself had created. The crater was not merely a scar. It was an engine of recovery, providing the warm, nutrient-rich conditions that allowed pioneer biological communities to establish themselves more rapidly than they could have in the cold, nutrient-depleted open ocean of the immediate post-impact years. The question of how the survivors in the open ocean maintained themselves through the darkest years of the impact winter is one that the fossil record answers only partially. The evidence from the Chicxulub crater suggests that survivor nanoplankton were present in the water column above the crater within days to months of the impact, implying that some photosynthetic organisms persisted through even the most severe phase of the darkness. How they survived is not entirely clear. The most likely explanation involves a combination of factors. The darkest phase of the impact winter was not uniformly dark across the entire planet, with some regions receiving somewhat more light than others, depending on the distribution of the stratospheric aerosol cloud. Some photosynthetic organisms may have been able to sustain minimal metabolic activity at extremely low light levels, and the deep ocean, which was less immediately affected by the surface darkness, may have harbored populations of photosynthetic organisms that could recolonize the surface as light levels recovered. The recovery of the base of the marine food chain was the prerequisite for everything else in the marine realm. And the Lowry et al. 2026, finding that new plankton species evolved within 2,000 years of the impact, means that the recovery of marine primary productivity was not simply a matter of the same Cretaceous plankton rebounding from a bottleneck. It was the beginning of a genuinely new evolutionary chapter. New species, not just recovering populations of old ones, populating the empty ecological space of the post-impact ocean. The marine world that emerged from the impact winter was, from the very beginning, different from the marine world that had preceded it. The selectivity of the KPG extinction, the pattern of which organisms survived and which did not, has been studied intensively for decades. And the patterns that have emerged are consistent enough to be considered established. Large body size was strongly correlated with extinction risk. Dietary specialization was strongly correlated with extinction risk. Dependence on living plant matter as a primary food source was strongly correlated with extinction risk. Calcareous shell or skeleton construction was associated with elevated extinction risk in the marine realm, particularly in the surface ocean where acidification was most severe. Conversely, small body size, dietary flexibility, detritivory or seed eating, the ability to burrow, ectothermy combined with low metabolic rate, and the exploitation of freshwater environments were all associated with survival. These correlations are not perfect. There are exceptions in both directions. Organisms with apparently favorable characteristics that went extinct, and organisms with apparently unfavorable characteristics that survived. But the patterns are robust enough that they cannot be explained by chance alone. The KPG extinction was not random. It was a filter with a specific shape, selecting for a specific suite of characteristics that would define the founding stock of the Paleocene world. The herptiles, the reptiles and amphibians were recovering in parallel. The crocodilians, which had survived the impact winter in relatively good numbers, were beginning to diversify into the warmer, wetter environments that the post-impact climate was creating. The lizards and snakes, which had also survived the extinction in reasonable numbers, were expanding into the warming world of the early Paleocene. The amphibians, whose sensitivity to environmental conditions makes them excellent indicators of ecological health, were recovering in the freshwater environments that had been among the most protected from the immediate effects of the impact. And in the oceans, the recovery that Lowry's team documented in the plankton was the foundation for the rebuilding of the entire marine food chain. New plankton species appeared within 2,000 years of the impact. The productivity of the surface ocean, its ability to fix atmospheric carbon through photosynthesis and to export organic carbon to the deep ocean, began recovering within thousands of years rather than millions. The fish that depended on the plankton recovered. The larger marine animals that depended on the fish began to recover. The marine food web, though fundamentally reorganized compared to its Cretaceous configuration, was functioning again within timescales that are genuinely remarkable. 100 years after the Chicxulub impact, the world was not yet what the early Paleocene would become. But it was no longer the shattered, dark, cold wreckage of the immediate aftermath. The darkness had lifted. The temperatures had recovered from the impact winter and had, in some regions, exceeded the pre-impact baseline as the elevated CO2 drove a brief hyperthermal. The forests were regrowing, though they were simpler and more open than the Cretaceous forests that had burned. The oceans were warming and repopulating with new species. The mammals were diversifying at extraordinary speed into every ecological niche that the extinction had vacated. The animals that would eventually evolve into the whales were still small hoofed mammals on the shores of the ancient Tethys Sea. The animals that would eventually evolve into the horses were still small, multi-toed forest browsers in the recovering forests of North America. The primate lineage had just appeared in the fossil record. the first small-eyed, grasping-handed tree dwellers exploiting the new world of angiosperm-dominated forests. And somewhere, in the burrows and root systems and dark soil of every continent, the ancestors of every mammal alive today were going about the business of inheriting a world that 100 years earlier had seemed entirely determined to kill them. The 100 years after the Chicxulub impact can be divided very roughly into 3 phases whose transitions mark distinct shifts in the environmental conditions that the survivors had to navigate. The first phase, roughly the first 5 to 8 years, was the acute crisis. This was the period of maximum darkness, minimum temperatures, and most severe acid rain. The stratospheric aerosol load was at its peak, reducing incoming solar radiation to perhaps 10 to 20% of normal values. Global average temperatures were at their minimum below the pre-impact baseline. The acid rain was falling with maximum intensity as the sulfate aerosols were progressively rained out of the stratosphere. Food chains on land and in the ocean were in their most disrupted state. This was the period in which most of the extinctions occurred, not in the first hours of the impact, but in the subsequent years as the food supply collapsed, and the survivors were reduced to whatever could be sustained by the detritus economy that replaced the photosynthesis-based economy of the Cretaceous world. The second phase, roughly years 8 through 20, was the transition period. The stratospheric aerosol load was declining as the sulfate aerosols were washed out of the atmosphere by the acid rain. Light levels were recovering, slowly at first, and then more rapidly. The acid rain events were becoming less frequent and less intense. Temperatures were beginning to recover from their minimum. But the food chains were still severely disrupted. The organisms that had died in the first phase were not immediately replaced, and the ecological communities that were beginning to establish themselves were simple, low-diversity pioneer communities, rather than the complex, multi-trophic structures of the Cretaceous world. This was the period in which the first post-impact ecosystem began to take shape, simpler, less productive, and less diverse than what it replaced, but functional. The third phase, roughly years 20 through 100, was the transition to the new normal, and it was characterized by a climatic surprise that the impact winter models had not always fully accounted for. The CO2 overshoot documented in the chemistry of the boundary sediments was now expressing itself as temperature. The cold world was becoming warm, and it was doing so faster than the organisms that had survived the cold had time to adapt. This hyperthermal, a period of warmth above the pre-impact baseline driven by the CO2 pulse, had its own consequences for the survivors. The organisms that had adapted to the cold of the impact winter now faced warming. The warm, moist conditions of the post-impact hyperthermal were, in some ways, ideal for the recovery of forests. Warm temperatures and elevated CO2 together promote plant growth. And the recovering forests of the early Paleocene benefited from both. But the rapidity of the temperature change, cold to warm, all within a century, was itself a selective pressure. The organisms that made it through both transitions, from Cretaceous warmth to impact winter cold to post-impact hyperthermal warmth, were the ones whose physiology and behavior were flexible enough to tolerate dramatic temperature variation in both directions. The mammals were particularly well suited to this thermal oscillation. Their endothermy, the ability to maintain a constant body temperature independent of ambient temperature, meant that they were buffered against the worst effects of both the cold of the impact winter and the warmth of the post-impact hypothermal. Their small size meant that they could exploit microhabitats that provided thermal buffering, burrows in the cold phase, shade and water in the warm phase. And their high reproductive rate meant that their populations could recover quickly from the bottlenecks that the temperature extremes had imposed. By the end of the first 100 years, the mammalian populations of the early Paleocene were already showing the rapid diversification that would, over the subsequent 10 million years, produce the full range of mammalian orders that populate the modern world. The birds that had survived, the ground-dwelling, seed-eating lineages that would give rise to all modern birds, were also benefiting from the recovering world. As the forests regrew and the insect populations recovered, the ecological opportunities for birds expanded rapidly. The loss of 3/4 of bird lineages at the KPG boundary had left an enormous range of aerial ecological niches empty, and the surviving lineages were already beginning to diversify into them. The extraordinary diversity of modern birds, more than 10,000 species today, traces its origins to the post-impact recovery that began within the first 100 years after the Chicxulub asteroid struck. The flowering plants, the angiosperms, were the dominant plant group of the recovering Paleocene world, and their dominance was a direct consequence of the KPG extinction. The gymnosperms, the conifers, cycads, and their relatives had dominated the late Cretaceous forests alongside the angiosperms. But the angiosperms, with their faster reproduction, their greater ecological plasticity, and their more diverse seed dispersal mechanisms, recovered from the impact winter more rapidly than the gymnosperms. The forests that regrew in the first decades and centuries after the impact were angiosperm-dominated in a way that the Cretaceous forests had not been. The world of flowers and fruits that we inhabit today was, in part, the product of the KPG extinction, a world in which the angiosperms, freed from the competitive pressure of the established gymnosperm-dominated communities, could demonstrate their superior recovery capacity and establish the dominance they have maintained ever since. Now let me tell you what I think about all of this. As someone who has spent time with the KPG boundary record and with the extraordinary research that has emerged in the past few years, the revision to our understanding of how quickly life recovered after the Chicxulub impact is one of the most significant developments in paleontology in recent years. The Lowry et al. 2026 study documenting plankton evolution within 2,000 years of the impact is not just a surprising finding about plankton. It is a statement about the fundamental resilience and adaptive capacity of life, about the speed at which natural selection can operate when the constraints of competition and established ecological hierarchies are suddenly removed. 2,000 years is nothing on a geological timescale. It is 80 generations of a human population. It is the entire span from the earliest urban civilizations to the present. And in that interval, in the darkened, acidified, recovering ocean, new species were appearing. This does not mean that the extinction was anything other than catastrophic. 3/4 of all species on Earth were eliminated. The loss of biodiversity at the KPG boundary was enormous, irreversible, and permanent. The specific organisms that went extinct, the non-avian dinosaurs, the ammonites, the mosasaurs, the pterosaurs, most of the marine plankton groups of the Cretaceous, are gone. They did not recover. They do not exist today. The extinction was real, massive, and final. But the recovery was also real, rapid, and extraordinary. The biosphere, stripped of 3/4 of its diversity, was not destroyed. It was reset. And the reset, the 100 years of darkness and cold and acid and heat that followed the impact, was not merely a disaster. It was, in the most precise biological sense, a filter. The most powerful evolutionary filter of the past 66 million years. It selected, with ruthless efficiency, for the characteristics that would define the age that followed. Flexibility, small size, dietary opportunism, rapid reproduction, and the capacity to exploit disturbed environments. The animals that carried those characteristics through the filter inherited the Earth. The mammals were not the most impressive organisms in the Cretaceous. By any measure of size, power, ecological dominance, or evolutionary success accumulated over time, the non-avian dinosaurs were more impressive. They had ruled the terrestrial world for 165 million years. The mammals had spent that same period hiding in the dark. But when the filter came, the hiders were exactly what the filter selected for. And the world that emerged on the other side of those 100 years was theirs. What I find most remarkable about the 100 years after the Chicxulub impact is not the catastrophe. Catastrophes happen. The geological record is full of them. What is remarkable is the speed of the response. The first new plankton species appearing within 2,000 years. The first mammalian diversification visible within hundreds of thousands of years. The crater itself becoming a hydrothermal refugium within days to months of the impact. Life did not wait for the world to become comfortable before resuming its experiments. It resumed them in the darkness, in the cold, in the acidified ocean, in the fractured rock of the impact crater. The experiments were simpler and more tentative than the ones they replaced, but they were underway almost immediately. The Chicxulub impact was the worst day the biosphere had experienced in 66 million years. The 100 years that followed were among the most difficult and most consequential in the history of complex animal life. And out of those 100 years came everything that has happened since. Every mammal, every bird, every flowering plant, every ecosystem, every organism alive on this planet today, including you. The darkness lifted, life resumed, and the world it resumed in was ours.